This video, we're going to discuss what Thevenin's and Norton's theorems state. Now, if you read the statement of the theorem, it says, any linear two-terminal circuit. Now, we really need to explain what this is. So we've mentioned what the linearity property is, and we've mentioned that resistors, capacitors, inductors will have the linearity property. They are linear circuit elements. And so as long as your circuit only contains resistors, capacitors, inductors, and sources, then it's going to be a linear circuit. By the way, there are some things out there that are nonlinear circuit elements that you may see in future classes, and there's only really one that we're going to see in this class, and that is an op-amp. In the lab, we will see diodes, and those things are generally not linear, at least overall elements. But for resistors, capacitors, inductors, we are good here. Now, what is a two-terminal circuit? So the idea is you have some sort of a circuit with sources and resistors and maybe another source and who knows, maybe more resistors. But the idea is you're going to have these two connectors drawn off of that, and those are going to be called the two terminals of your circuit. The easiest way to think of what we're talking about here is look at an outlet in your wall and plug a device into there, right? There's your two prongs there on your plug, and you're plugging it into the two places in the outlet. That's your two terminals joining the two different circuits together, the circuit that is your device and the circuit that is your house electricity. So you're plugging in there, it's your two terminals there. So any circuit that has only, resistors. Now, for us in this chapter, we're only going to have resistors, but there is a version of this that can work with inductors and capacitors. But let's just say resistors here and sources, and you have to have these two terminals marked off to say where you're plugging something in, essentially. And anytime you have that type of circuit, a linear two-terminal circuit, no matter how complicated it is, no matter what way you have your resistors and sources hooked up, no matter if they're independent sources or dependent sources, if things are in series and parallel, no matter what, this theorem guarantees that you can find an equivalent mathematical circuit where you replace all that complicated stuff with simply a single voltage source in series with a single resistor. And we call the voltage source value VTH for the Thevenin voltage, or Vthevenin, and RTH would be the Thevenin resistance. So again, Thevenin's theorem is just saying that no matter what circuit you have that's only, in this case, resistors and sources, in whatever complicated fashion, as long as you identify two terminals, you can find a mathematically equivalent circuit with all of that to being a voltage source in series with a resistor. Norton's theorem is incredibly similar. Again, any linear two-terminal circuit is equivalent to, in this case, instead of being equivalent to a voltage source in series with a resistor, it is equivalent to a current source in parallel with a resistor. And so, really, you just use Thevenin's theorem and apply source transformation, you get Norton's theorem, and that's all there really is to say here. And as a result of the fact of source transformation, that means your Thevenin resistance is equal to your Norton resistance. So it's the same number there for both of them. Again, this theorem by itself is maybe not practical. All it says is that there is some circuit you can simplify it down to, but we'll have to see in later videos how do we actually find that simplified circuit.